Okay, so welcome to the final part of uh, S25. Okay, so here we are going to be seeing a pseudocode for S25. Of course, this is all going to be uploaded to the uh, folder. So of course, I start the program, define constant, and then I initialize file, all standard stuff. Then I compute the distance. Uh, and then I store it as a function. And then uh, I'm going to actually store the message positions, then define cascading reactions uh, and everything. Uh, yeah, so again, anyone can access this, but let us look at the actual code and see what is going on right here. Of course, the standard import stuff. I'm initializing my uh, stuff. So, and then I'm going to like look at the distance, the very first thing which I'm going to do. Yeah. So, first thing I'm just going to do is I'm going to compute the Manhattan distance. I'm going to define a function which does that. Then I'm actually going to be doing storage array. So what it does is it takes an A3, Q and A. So A3 is going to be another array, Q is going to be the position, and then A is going to be the file. So it actually stores all of the positions in A3 and returns the respective position of particular queue. Okay, yeah, so it's very standard stuff. Then I'm going to be looking at storage array one. Yeah, so I'm also going to be defining storage array one. Of course, I can just put in an if statement here and return s of q or uh, k. So essentially, what this does is it gives me the number of uh, positions of A3. Uh, and then, of course, I'm going to define LRM uh, and then actually define the dictionary itself. So this contains all of the relevant text. I mean, this does sit in the subject verb object form. And of course, if it is an odd number, then if it's an odd if, uh, it is going to be a subject, and then if it is even odd, then it's going to be a verb. Uh, okay, so then define minimum distance. It actually takes this LRM, and then it actually takes a message and then returns the minimum distance. And also, it kind of something similar is going to be um, making the storage part of this. Okay, so message allocator. So what this does is it takes in a particular element, and of course, QMod is going to be my. Did I define it here? No. So QMod is actually going to be defined here. Okay, um, and then it's just going to allocate everything into the QMod. So what this QMod is supposed to hold is all of the alarms which are the closest to the given message. And then it's going to return the actual QMod. And also I can make a version of this to actually return the number of rows. Then I'm going to do an LRM check. This result returns the closest instance to given LRM in the particular state itself. Okay, so that's all the definitions. Uh, yeah, this file will also be available in the thing. Okay, so now let us look at the actual main or the execution part. So I'm going to put this as my file size. So it contains 1, 2, 3, 4, 5, 6, 7, 8, 8 zeros. Again, this is going to take just a few seconds to actually generate. Uh, and what this does is this actually looks out for the execution without actually executing it. But it also returns what is the space that I'm looking at. So for example, the attacker space, how many rows are there? In the receiver space, what are the rows? And then how does the cascade function look like? And also, um, yeah, it also returns the number of rounds. So let us see how it looks like. Of course, I'm using Python. So let's just run it. And as I said, the main bottleneck here is the file creation process. So right after the file is being created, we get a message called generated file. Let me just check where it is. Yeah. And then it actually returns the A. And of course, this is going to take almost a minute. Again, so if any of the uh, software people look at the code, it is not going to be in an optimal state. I apologize for that, but I may somehow managed to make it work. And of course, this is just 8 zeros. Then I should be looking at something like 9 zeros, yeah, to be ideal. So again, 9 zeros is going to take a long time to actually generate. And this file size is the main bottleneck for this. As you can see, right after this, everything else would go on much more simpler. Okay, so now let us look at the issues. So first thing is, why do I need d type equal to np dot int8? So the actual integer is going to be a few bits, I mean like few bytes longer. Uh, int8 confines it, and then I can, the file generation process is going to be much more convenient and it's going to be faster if I just use int8 and not some like int16 or int64, etc., etc. Uh, that is one of the main reasons I think there is a bottleneck. So if I do write this in assembly, maybe I can uh, get this down to something like, yeah, integer of 2 bits, and that should be much faster. Or I can use a GPU clustering or multi-threading or something like that. So yeah, it has begun, and we have received one of the message. Okay, so there's a lot to unpack. So let me just. Yeah, this working. Okay, so this is what we are looking at right now. Of course, we have the file generation. It's going to be whatever message that I'm actually trying to generate. Of course, I cannot show the entire thing. Maybe I can write it to a file and then post it later on. So the first instance, I'm going to be choosing the message 212013. Yeah, this is the first snippet, so there's actually no LRM. And this is the message which is being sent. So AC, whenever there is an A in front of a character, that means it's the attacker. So the attacker sees this. So again, if we look at it, we have one bit of ambiguity. Yeah, and of course I have the actual message one. And then what am I looking at here? L23. So what this represents is going to be the number of instances where this message is being repeated. Yeah. So in A, we have in A, which is this file, we have 23 messages which are repeating. And for attacker L, we have these many numbers. So it's 23, 25, 17, and 28 instances corresponding to each of the things. So the positions are of course stored here, and uh, this part is just zeros, but these are the actual array positions which are storing it. Okay, so we are going to begin the cascading. Message repeat is 23. States are this. And then so the next instance is going to be this particular thing, which is not LRM valid as of now. But what message I'm sending to the receiver is going to be 300112. And then we look at the positions which have valid instances, which are like very close to this. So of course, there are going to be some. Um, and then the number of message repeat is 4. So there are 4 instances where I get something which is actually close to this. Um, and then, of course, I have updated the states. And then we get the actual stuff here. Uh, so now let us look at what happens to the attacker. I mean, we did see it. Um, I can just write some code here to check what happens to the attacker. Let's see. Uh, state. I think that should be fine. Let us just run this. So of course, with 9 digits, it's going to take exponentially longer. Um, and what we did see is the generating file is the one which is the bottleneck. So that's the reason I suggested using a large library of already, somewhat unoptimized things. So with movies, the problem is uh, when we look at the nature and when we look at how the um, I mean, if you look at the pixels in, let's say, a naturally captured photo, there is going to be these clusters which are going to be formed, which are going to be extremely predictable. So they are actually not random, and they are kind of not very well used. Um, just a second, I have to. We will also look at what happens to the uh, number of instances. Okay. Sorry for the delay because yeah. So one of the major disadvantages that you have to of this particular implementation is that you have to keep generating the files over and over again. I'm not even going to go to the qubit kind of implementation because the qubits are actually quite fragile as of now. And then just repeatedly using them for slightly better random function is really not ideal. Uh, Yeah, so originally it would have taken, I think, around 3.3 billion years with something like English, just because of the file size and even just the very first iteration that is going to be taking maybe a few hundred million years or so. Um, and then it's really not possible for me to do anything, even with the GPU clustering and also using something like a supercomputer. Uh, it is actually not that much feasible. Okay, so let's just wait for this. Yep. So right after generating the file, the message is going to be printed. And of course, the cascading is going to take a little bit of time. Yep, and the cascade is done. Compared to generating the file, these kind of things seem very, very quick. Okay, so the last one is what we are going to look at. Before that, let us look at what exactly is happening. What are the changes I made? Uh, these two numbers specifically. So the attacker sees 15 states and um, the receiver sees 2 states. And at the very end, I see the receiver sees 1 state and the attacker sees 3. So what happens is uh, in A, let's say I have the 57,000th position uh, as my particular instance. What happens is uh, the next bit is going to be defining my master key. So whatever message I send, so again, whatever message I've sent, whatever the message is, this has nothing to do with the key, uh, and it is just because of that it is going to be extremely hard for the person who's looking at it to come up with anything. Okay, so let me just see if I've covered everything. It looks like I have. Mm, Yeah, I mean, we could try adding another zero just for fun. Uh, that is actually intended metric. So even though it is around 30 MB, it is it is just not happening. So if I were to run this, it is just going to take forever. All of these are going to be uploaded to Google Doc. Um, yeah, so one can do with just the array, or and that is the thing. Uh, so there are going to be some performance metrics that I want to uh, kind of show, which I'm not going to be showing it right now. The first one is going to be the file size generation versus the time taken. Second one is going to be, of course, the attacker versus receiver states, the numbers specifically. And the third one is going to be the final ratio of everything. Uh, that is just going to be the one of the parts. And then what I'm planning to do is I'm planning to make a separate file where I include the generated file, and I'm going to include series of messages. And then what I can do, right, is to use TensorFlow uh, and to generate a model, a training model, which would look at all of these things and then try to learn by itself. Then what I'll do is I'll just switch over to the attacker's perspective, and then I can look at the accuracy in which the keys are guessed. Again, this is for a near omniscient case. So the 3-1 is for near omniscient case where I'm using the MMI MMI -1 criteria. And again, this is for one specified bit. If we look at something like one specified bit, but um, uh, there's no information on where the actual bit is, then the number just skyrockets. So whatever we have here, we are going to get around six times of that. So let's see. So we have 26, and then we have just 1, 2, 3, 4. So we are going to be getting 4 times 6 for all of the digits. And then what we are going to be seeing at the very end is 1 and something very high. So this is 3 into 6, which is 18. So out of those 18 instances, if there is collision between any of them, then I have successfully gotten the key. And now one more security measures which I want to raise here is right after generating the file, and let's say after all of these messages, I can just move ahead with my communications. And when a person looks at it, when an attacker looks at it, it is going to be almost impossible to guess exactly where I am. especially with multiple messages post key distribution. Um, so that means the resources used are going to be extremely low compared to, I mean, ideally it should be at the same level of BB84 when you scale it to infinity. Um, but yeah, so let's say that the final message is mm, okay, so at 13,065. So what my next message, so the actual message, or let's say I want to include as um, some other LRM. Uh, what I'll do is I'll just start from the 13,066th position, and then every subsequent message is going to be an extension of that. So even if you miss one single message, let's say if the messages are of different length, if the attacker misses even one message, then guessing the next message is again a hassle. There is going to be you have to look at all of these states, and then it would just get messier. And if you were to um, if the attacker were to miscalculate something, for example, number of messages or length of the message, maybe a bit got intertwined in the wrong way, or a bit is missing, uh, then following the chain of um, the chain of messages is going to be very, very hard. And that is exactly what I was going for in my S25. So yeah, again, by the time I stop talking, maybe this might this might actually generate. Um, yeah. So for four of them, if I want to make something meaningful, it is going to be 9 zeros or maybe even 10. Uh, and for something like uh, let's say 8-bit, that is going to be much, much higher, especially when I consider the entropy. So the entropy of this is going to be, I think, uh, let's see. Again, I just have to calculate the entropy of this particular language. Four, 64, power 6, then 4 to the power 3. So it's around 1 over 64, I think. So entropy per word is going to be 4 times 4, that is 16, and 4. So it's 1 over 4 entropy per word. Entropy per letter is going to be much more lesser. It's one of them is okay. Um, Again, I really wanted to show what is going to happen with these many zeros, but apparently it is not letting me. Oh yes, so after this, what I can do is I can use Qiskit and simulate some sort of a noise protocol and error correction codes, and how they're actually going to affect this entire premise. And I think that is it. So uh, okay, so we did see how everything works, and we did see this. Everything is going to be posted on the actual file, and I'll see you guys when I see you guys. Thank you.